GitLab lets you host repos, do merge requests, track issues, scan for vulnerabilities. Unlike GitHub, whose stack is built with plugins, GitLab ships all of this as one big open source app. What actually happens behind the scenes when you push up your code though? Let's find out. We'll start with an overview of the architecture and the stack, then we'll take a closer look at the CI flow to understand what's really happening in the pipeline behind the pipeline. Finally, we'll touch on how all this might change very soon. GitLab is a monolith built with Ruby on Rails. This is the whole architecture, and we're going to break it down into 3 flows: the client to the ingress, ingress to core, and core to externals. After a request gets through the firewall and load balancer, it's sent to Nginx, which terminates TLS, serves stack files, and enforces rate limits. Nginx is intentionally thin here. It just gotta be a fast, reliable conduit to the core services. If you're a real hacker though, GitLab actually lets you bypass Nginx entirely by using GitLab shell. This service lets you connect to your instance using port 22 and a public key. It feels like a shell, but sadly, it's really just a small Go app that pretends to be one. It never actually gives you root access, and it only accepts Git specific commands. Sorry. Once a request passes through either Nginx or the shell, it reaches Workhorse. Workhorse is just one of GitLab's many fancy names. It's really another simple Go service that handles slow and heavy I/O so the web server doesn't have to. For example, it handles streaming logs, large file uploads, and downloading artifacts. These things are either too I/O demanding or too unique to be pushed into the core service. The next player we need to know about is Puma. The HTTP server is where GitLab stores all its business logic: auth, database, cache, background jobs, rendering, and of course, Git operations. They use Puma, a Ruby web server that supports multi-threading. Now, Ruby has a global interpreter lock, which makes it a memory hog. This started causing memory leak problems for GitLab. So by using a multi-threaded server, GitLab started using their shared memory more efficiently. When I/O causes a thread to pause, for example, another thread can continue with its request. Swapping their single-threaded web server for Puma reduced memory by 40% alone. Another design decision was to keep these Puma services stateless, meaning no important data lives on the Puma host. Sessions, for example, are on Redis, and this makes it easy to reconstruct data if a Puma node goes down. Keeping these stateless requires some discipline, but the payoff is that it's easy to scale horizontally. You just got to add more Puma nodes behind the load balancer, and throughput increases linearly. Not everything needs to happen right away. No one's waiting around for a notification email or for their CI log to be archived. This type of work is perfect for background jobs. GitLab uses a Ruby framework called Sidekiq as its background worker. It runs as a separate process, pulls jobs from a Redis queue, and works on them independently. So when Puma wants to start a background job, it just drops a JSON payload into Redis. The Sidekiq workers are sitting in a loop watching Redis. They pick up the job, run the Ruby code, and either mark it complete or retry it on failure. So when you comment on an MR, for example, Puma enqueues a notification job and immediately returns a 201 to your browser. Meanwhile, Sidekiq is off in the background, getting recipients, sending emails to them, and doing the slow stuff. Remember that Puma is stateless. It doesn't hold on to data. Everything gets delegated to a set of external services, so let's check those out now. In the early days, GitLab stored repos on a shared network file system. Every Puma and Sidekiq node would mount the volume and run Git commands directly on disk. That's fine until it isn't. Eventually, latency spiked. Also, they couldn't see what Git operations were running and causing the slowness. Not good. So they built Gitaly, another fancy name for a service that owns all the Git data. Instead of running a Git command on a shared file system, you send a remote procedure call to Gitaly, which translates that into a Git operation. For example, to get a diff, you call this, and Gitaly returns the diff hunks. To list branches, you call this, and Gitaly reads from disk and returns a result. To push, call this, and Gitaly will write the objects, update the refs, and run server-side hooks. You get the idea. Every Git operation is a discrete typed RPC. This means Gitaly can be monitored, load balanced, and scaled. All the structured data lives in Postgres. Users, projects, groups, issues, merge requests, pipelines, permissions, all of it. But GitLab doesn't connect to the big elephant directly. It goes through PgBouncer first. PgBouncer is a connection pooler that takes hundreds of simultaneous connections from Puma and Sidekiq nodes and multiplexes them down to a manageable pool. Without it, the fleet would hit Postgres' connection limit almost instantly. GitLab also uses read replicas, which are secondary Postgres nodes that receive a streaming copy of all writes from their primary. This lets them route read-heavy operations like loading a project's issues to replicas so the primary can focus on writes. For high availability, they use Patroni, which handles leader election and automatic failover. So when the primary goes down, Patroni picks a new one and lets the service registry know the winner. Then PgBouncer picks it up without any human intervention. Redis is where things get interesting. GitLab has 8 separate stores in Redis. There's one for Sidekiq job queues, cache data, shared state, background job queues, sessions, pub/sub, rate limiting, tracing, and a repo cache. On a small self-managed install, one Redis can handle all this. On a bigger one like GitLab.com, these are fully separated clusters. A few more supporting players worth knowing about now. As much as GitLab loves Postgres, not everything fits into a row. CI artifacts, container images, attachments, these blobs can be gigs in size, so GitLab stores them in object storage like GCS or S3. Then a simple pointer is stored in the database. Duo is the umbrella name for GitLab's AI features. Code suggestions, chat, root cause analysis, all these funnel through a gateway, which is just a Python service that routes requests to the right model. Claude for code gen, Vertex or self-hosted models for other things. And this gateway means GitLab can manage rate limiting, cost accounting, and model swapping all in one spot. Sidekiq dispatches emails using a Ruby library fork. LDAP syncs enterprise users. Kubernetes manages deployments. And webhooks send requests to your endpoint when something interesting happens. Those are the main players. But how do they all work together in prod? To answer that, we need to look at GitLab's most interesting feature, the CI pipeline. A lot has to go right between when you git push and when you see that green check. The whole thing's a 3-step process. First, your YAML gets parsed and compiled into a job graph that lives in Postgres. Then runners pull for work and pull jobs off that graph. And finally, a merge train checks whether your changes will break things. GitLab receives your pack data, stores it, and fires a post-receive hook. That hook kicks off the Rails pipeline service. Rails fetches the YAML and runs it through several passes. First, any include directives get resolved, local files, project templates, remote URLs. Then variables like these get interpolated. Then rules only and except keywords get evaluated against the pipeline context to figure out which jobs actually apply. And after all that, the job gets written to Postgres. One row for the pipeline, a few for the stages, one for the job itself, and some extras for the relationships between jobs. Here's conceptually what things look like in Postgres. At this point, GitLab can stop worrying about the YAML and treat Postgres as a source of truth. Even though a job is in the database like this, it's not in the runner queue yet though. That's why we need the worker. This Sidekiq job evaluates the graph, finds all jobs whose dependencies are satisfied, and transitions them from created to pending. Pending means it's in the queue, so runners can finally see it now. GitLab runners are little Go binaries that are eager to work. They connect to your GitLab instance and pull for new jobs every 3 seconds. On each pull, Rails queries Postgres for pending jobs that match the runner's tags. Once it finds a match, it transitions that job from pending to running. Then the runner gets back the full job payload. Environment variables, Docker images, scripts, artifacts, everything it needs. The runner executes the job and streams logs back to GitLab in real time. Then the pipeline service finds the next set of jobs and transitions those to pending. The cycle repeats until every job is done. The pipeline gets its final status, and then that beautiful green check appears. Pretty simple when there's just one dev, but what happens when hundreds of devs are firing off MRs at the same time? GitLab has to do a lot more coordination to keep things running smoothly. Let's take a closer look. Hey, it's Tyler, and these first initial videos have all just been sponsored by me. If you work for a company who you think would be a good fit for this channel as a sponsor, either for the YouTube or the newsletter, send them to this link, and I'd love to hear from them. And for everyone else who's enjoying this, just send it to a buddy at work. That'll help the channel grow. Cool. Let's get back to it. Thanks. The simple question you ask your CI every time you push is, will my changes break main if it merges right now? Normal pipelines do that by creating a temporary commit that merges your branch into main and then following the flow we just covered. The trickier question is, will my changes still work if everyone else merges first? On a busy team, two branches that each pass CI individually might conflict when they both merge into main. GitLab solves this by testing the future state of main, not just the current one. They call this a merge train, and it works like a queue. When you add your MR to the train, GitLab creates a pipeline that tests your changes on top of every MR ahead of you in the queue. The beauty is that the dev behind everyone else doesn't have to restart anything manually. Devs have peace of mind that their changes will work against the actual main when they merge, and not just the one that existed when they first created their branch. One trade-off is that this is a premium feature. Another is that flaky tests become everyone's problem, because a single unreliable test can destabilize the whole train and make things complicated. Although this style of CI is kind of new, the foundation of ideas behind it was built in the 50s and 60s. Let's start with pipes. In 1964, Douglas McElroy wrote a memo at Bell Labs about how programs should be, quote, linked like a garden hose, interchangeable components connected through data streams. Which sounds good, but the idea sat dormant for nearly a decade before Ken Thompson implemented pipes as a core Unix feature in 1973. Pipes is what makes these simple commands work. Using the output of one command as the input of the next. Probably sounds familiar, right? This is the foundation of every CI pipeline ever run. It's also the idea behind GitLab's stages keyword, where you break your build process into steps, run them in order, and let each phase's artifacts flow into the next. Also, pipes are the idea behind AI agents, but that's for another video. Even before CI existed, engineers building chemical plants and missiles had the same problem. How to efficiently schedule dependent tasks. Their answer was the directed acyclic graph. It's a graph of dependencies with no cycles, where the nodes give you a valid execution order. This is where the critical path idea comes from, which is the longest chain of dependent tasks in a graph. Once you have this, you know what to parallelize without slowing down the overall timeline. The specific algorithm is Kahn's topological sort, and it goes like this. Repeatedly select nodes with no incoming edges, emit them, remove them from the graph, repeat. Every CI scheduler ever does some version of this. GitLab's is the needs keyword. Here, unit tests and integration tests can start right after build finishes, while deploy waits for both of them. Nothing is waiting for anything it doesn't actually depend on. Under the hood at GitLab, a service runs Kahn's algorithm on every status change, which means a 1962 algorithm running inside a 2026 DevOps platform every time you push. Pretty cool. Now for the concurrency problem. If hundreds of runners poll for jobs every 3 seconds, how do you make sure the same job doesn't get handed to 2 runners at once? The the naive answer is to use a lock. Before picking a job, lock the table, grab one, mark it as running, and then unlock. And that works, but it also tanks throughput because all the Rails processes would be constantly waiting around for the same lock. A more creative answer came in 1981 under the name optimistic concurrency control. The premise is that conflicts are rare, so don't lock preemptively. Just proceed without locking and detect conflicts at commit time. GitLab does this with a lock version column in the build table. If another process already claimed this job, lock version would have incremented so the where clause would match 0 rows, Sidekiq would return a 204, and the runner would chill a bit, but then retry again in 3 seconds. This is really clean because you don't need a global lock. You get speed with just a version number, and all it costs is one failed query and one poll cycle. Not a bad deal. So that's how things work now and where these ideas came from in the past. But is this how it'll work in 5 years? 5 months? I don't think so. Everything about the CI process assumes a human pushes code and stares at a pipeline page, twiddling their thumbs until a green check shows up. And that workflow is starting to feel old. If I have a bunch of agents working in a bunch of work trees at the same time, why would I make them all push up their changes into some cloud and then coordinate a complex merge train? My prediction, the primitives of pipes, DAG, and OCC will stay around for a while, but the workflows built on them will look very different. Whatever happens though, one thing's certain, we'll still need a fast and reliable way to evaluate our code. You now know how GitLab helps us do that today, and I hope this foundation helps you navigate the CI changes of tomorrow. See you next time.